Alright, so far we have talked about the first 7 topics. For each of the functions here, we discussed their definitions, graphs, domain, range, x and y intercepts, and so on. And today we're going to have a look at the next type of functions, which is trigonometric functions and all related concepts. Okay, first of all, in defining the trigonometric functions, we need to know some related concepts. For example, reading measures. The reading measure of angle theta is defined as the length A of the arc that subtends the angle divided by the radius r of the circle. So the reading measure of angle theta equals A over r. Okay, and also make sure you know how to convert between degree measures and radian measures. Basically, we have 2 pi equals 360 degrees, right? So pi equals 180 degrees. So as long as you remember this, you should be fine in converting between degree and radian measures. For example, if I ask you, what is the reading measure of 50 degrees? Then you should use this, pi. Pi is 180 degrees, right? We don't know the reading measure of 50, so we can let 50 degrees equals x in reading measures, or x readings. Then pi over 180 degrees should equal x over 50 degrees, right? Therefore, you can easily solve x equals 5 over 18 pi. So that's the reading measure of 50 degrees, right? You get it? Of course, you can also use this formula to convert between degree and radian measures. Okay, next, let's have a look at some commonly used angles in radian measures. For example, 0 degrees is 0 radians, right? 30 degrees is a 6th pi. 40 degrees is a quarter pi, right? And 60 degrees is a third pi. And also have a look at other degree measures and their corresponding radian measures. And of course, we also know 360 degrees is 2 pi, right? These are commonly used angles in radians. And then let's have a look at the definition of trigonometric ratios in a right triangle. If you have a right triangle, and suppose we have acute angle t here, then sine t is defined as the opposite side over the hypotenuse side, Cosine t is adjacent over hypotenuse. Tangent t is defined as opposite over adjacent, right? And these 3 ratios are called primary trigonometric ratios. As long as you know the primary ones, then the secondary ones can be easily evaluated using the reciprocal of the primary ones, right? And also Pythagorean theorem tells us that opposite squared plus adjacent squared equals hypotenuse squared. And also actually we can extend this definition to any angle in the 2D Cartesian plane, right? Again, before we dive to the trigonometric ratios definition in 2D Cartesian plane, let's have a look at some related concepts. So usually we can have any angle in the 2D Cartesian plane. Usually we'll use the positive direction of x-axis as initial arm of an angle. Then the terminal arm of an angle could be anywhere. For example, in one of the 4 quadrants, or either in x or y axis, right? So if we consider this angle as turning from initial arm to terminal arm following a counterclockwise direction, then you will have a positive angle. Otherwise, if you consider this angle is from initial arm to terminal arm following a clockwise direction, then you will have a negative angle, right? And also, angles with the same terminal arm are called coterminal angles. For example, this angle could either be expressed as 135 degrees or 3/4 pi, or it could also be expressed as -2 to 5 degrees or -4/5 pi, right? And we can use, for example, 4/4 pi plus 2k pi to express the same angle, to express all the angles with the same terminal arms here, where k belongs to the integer set, right? Okay, then we can define trigonometric ratios for any angle in the 2D Cartesian plane like this. So suppose we have an angle like here. The initial arm is on the positive side of x-axis, and this is its terminal arm. So we can choose any arbitrary point on the terminal arm of this angle. For example, P, with x and y coordinate as x and y. The distance between P and O is denoted as r. Then sine alpha is defined as y over r. Cosine alpha is defined as x over r. Tangent alpha is defined as y over x. Cosecant alpha is defined as r over y. Secant alpha is defined as r over x. Cotangent alpha is defined as x over y. And of course, sometimes some of these ratios are not defined if the denominator is 0. And it's obvious that coterminal angles will have the same trigonometric ratios, right? Okay, specifically, if you let r equals 1, then we could also use unit circle method to define these trigonometric ratios. For example, if you let r equals 1 and make a unit circle, then we can choose a point of intersection between the terminal arm and the circle. Then in that case, sine alpha equals y over r, where you have r equals 1. Therefore, sine theta just equals y, right? And cosine theta equals x, and tangent theta equals y over x. You see that? And these are the trigonometric ratios of some special angles in the interval from 0 to 2 pi. Make sure you have a look at these angles. Actually, you don't have to memorize them using Google first, because we have already been familiar with these angles in the first quadrant, right? There are 5 special angles in the first quadrant: 0, 6 pi, quarter pi, third pi, and half pi. Make sure you know the 3 primary ratios: sine, cosine, and tangent of each of these angles. And for other special angles in other quadrants, you can just use the property of symmetry to help you to evaluate the trigonometric ratios. For example, if you want to evaluate the trigonometric ratios of this angle, 7 pi over 6, we know that we can find a corresponding angle which is symmetrical with 7 pi over 6 in the first quadrant here, a 6 pi, right? The terminal arm of 6 pi and 7 pi over 6 are symmetrical in the x-axis. In the origin point, right? Therefore, their sine should be opposite to each other. So we know sine 30 degrees or sine of 6 pi equals square root 3 over 2. Then we must know the sine of 7 pi over 6 should be opposite to this value, which is negative square root 3 over 2, right? And their cosine are also opposite to each other. This is a cosine. The cosine are opposite to each other, which is square root 3 over 2 for a 6 pi and negative square root 3 over 2 for 7 pi over 6, right? And their sine are also opposite to each other. For example, sine 6 pi equals 1 over 2, and cosine and sine 7 pi over 6 is negative 1 over 2. But their tangent are equal to each other. Square root 3 over 3 and square root 3 over 3. Because tangent is just the ratio between sine and cosine. If they are symmetrical in the origin point, they will have the same ratio between y over x. You get it? Alright, next let's have a look at some properties of trigonometrics. Okay, so we'll divide trigonometric identities into 3 parts. Part 1 can all be found in a diagram called magic hexagon. So basically you can draw a hexagon like this and then put sine, cosine, tangent, cotangent, secant and cosecant in this order. Then we can find the following identities: reciprocal identities, quotient, product, Pythagorean, and cofunction. So let's have a look at each one of them. First, reciprocal identities. All of the reciprocal identities can be found by going through the one. For example, if you go through the one from sine to cosine to cosecant, this will help you memorize the relationship between sine and cosecant. Actually, they are the reciprocal of each other, right? And similarly, cosine and secant are reciprocals with each other. Tangent and cotangent are reciprocals with each other. Therefore, we have a list of identities on the right. Next, quotient identities. We can follow around the clock in either direction to get all the quotient identities. For example, if you start from here, tangent x equals sine x over cosine x. Or you can go the other direction. Tangent x equals cosecant x over cosecant x. And for example, you could also start from here. Cotangent x equals cosine x over sine x. And therefore, we have the following 12 quotient identities, right? Each one of them can be found in the magic hexagon. Okay, next, product identities. The reciprocal identities and quotient identities can also be summarized by product identities. The hexagon shows that a function between any two functions is equal to them multiplied together. If they are opposite each other, then 1 is between them. And then we have the following product identities listed as listed on the right. Alright, next, Pythagorean identities. If we go clockwise around these 3 inside triangles starting at the top and using addition, then we'll have 3 Pythagorean identities. Again, I'm not gonna prove this for you here. You can try to prove this by yourself after this class. So this magic hexagon will help you to memorize this relation. First, if you consider this little triangle here, we have sine x squared plus cosine x squared equals 1, right? Then if you consider this little triangle here, tangent x squared plus 1 equals secant x squared, right? Then if you consider this little triangle here, you will get cotangent x squared plus 1 equals cosecant x squared. Alright, next, cofunction identities. If we go across the hexagon either left to right or the other way, then we'll have the following cofunction identities. For example, sine x equals cosine half pi minus x, tangent x equals cotangent half pi minus x, and then secant x equals cosecant half pi minus x. Again, we can use the definition of trigonometric identities in the 2D Cartesian plane to prove any one of these identities. I'm not gonna do this here for you. You can try this at home and let me know if you have any questions, okay? Alright, so that's the first group identities, or part 1 of the identities. Next, let's have a look at the second group of the identities, which includes the trigonometric identities featuring negative theta and trigonometric identities featuring theta plus half pi times a integer k. So in a summary, these are the identities in the second group we need to memorize. Okay, so we'll explain this one by one. So first, trigonometric identities featuring negative theta, which provides a way to evaluate any trigonometric identities that includes negative theta. For example, we can easily prove negative theta equals sine negative theta equals negative sine theta, cosine negative theta equals cosine theta, or tangent negative theta equals negative tangent theta. So I'll give you a brief explanation here. Okay, so suppose we have a theta here. The initial arm is on the positive side of the x-axis. Terminal arm could be anywhere. It could be either in the first, second, third, or fourth quadrant, or on the x or y axis. So we'll just have a look at the case where the terminal arm is on the first quadrant here. So for other cases, the method should be the same. So if you choose a point on the terminal arm of theta, so let's call P the point. Let's call the point P with coordinates x and y. Then negative theta must be here, right? Then there must be a corresponding point P prime with coordinates x and negative y on the terminal arm of negative theta, right? So according to the definition of trigonometric ratios, sine negative theta equals the point, the y coordinate of the point on the terminal arm, which is negative y, over the distance between this point and origin point, which is r. So that is negative y over r. What is y over r? Y over r is actually sine theta. That's why we can prove sine negative theta equals negative sine theta. Did you get it? And similarly, you can also prove cosine negative theta equals cosine theta, and tangent negative theta equals negative tangent theta. Alright, so next, trigonometric identities featuring theta plus half pi times k. So that means if you have a angle theta, any angle theta plus half pi times the integer, how can we simplify this? So we'll have a look at the cases separately. First, when k equals 1, then you have theta plus 1 half pi, right? So let's have a look at the first diagram here. Suppose the terminal arm of theta is in the first quadrant. Then where is theta plus half pi? Theta plus half pi must be somewhere here in the second quadrant, right? And we know this angle here is 90 degrees or half pi. So if you choose any arbitrary point P on the terminal arm of theta whose coordinates are x and y, then after you turn that terminal arm for half pi, P will come here, P prime, whose coordinates are negative y and x. You see that? Because these two little right triangles are congruent, right? Therefore, the length of this side should equal the length of this side, and the length of this side is x. Then we know the length of this side is also x. Therefore, the y coordinate of P prime is x. And the x coordinate of P prime is negative the absolute value of this length. So what is this length? This length equals this length, which is y. Therefore, that's negative the absolute value of y. Apparently, y is positive, so the x coordinate of P prime is negative y, right? And then, using the definition of sine, cosine, and tangent, we can easily evaluate the three trigonometric ratios of theta plus half pi, right? Therefore, we have sine theta plus half pi equals y coordinate x over the distance between that point, P prime, to the origin point r, which is x over r. So what is x over r? X over r is the cosine theta in the original angle, right? Therefore, sine theta plus half pi equals cosine theta. Cosine theta plus half pi equals negative sine theta. Tangent theta plus half pi equals negative cotangent theta. Did you get it? Okay, next, let's consider cases where k equals 2. When k equals 2, you will have theta plus pi, right? So again, let's have a look at the first diagram. For other cases, you can basically use the same method. So suppose theta is in the first quadrant. Where is theta plus pi? Theta plus pi will be in the third quadrant like this, right? So this is pi or 180 degrees. Again, if you choose a point P on the terminal arm of theta, whose coordinates are x and y, then if you turn theta for another pi, then P will become P prime, whose coordinates are negative x and negative y, right? Can you see that? Because they are symmetrical in the origin point. And therefore, if you consider this angle here, sine of that angle equals the y coordinate of that point over r, which is negative y over r. And y over r is sine theta. Therefore, we have sine theta plus pi equals negative y over r, which is negative sine theta, right? And similarly, cosine theta plus pi equals negative cosine theta. And tangent theta plus pi equals tangent theta. You get it? Alright, so if you know the cases when k equals 1 or k equals 2, then it's not difficult to evaluate the cases where k equals 3, right? For example, if k equals 3, we have sine theta plus 3 pi over 2 equals, what we can rewrite this to sine theta plus half pi plus another pi, right? So if you can then consider this is a angle, for example, beta, then we know sine beta plus pi equals negative sine beta. So this is your beta, right? And then evaluate sine theta plus half pi. We know sine theta plus half pi is cosine theta. So that's why eventually you will have sine theta plus 3 pi over 2 equals negative cosine theta. You see that? So using the result from k equals 1 and k equals 2, you can easily evaluate cases where k equals 3. Alright, so when k equals 4, we can easily see theta plus 2 pi is actually coterminal with theta, right? Therefore, sine theta plus 2 pi equals sine theta. Cosine theta plus 2 pi equals cosine theta. Tangent theta plus 2 pi equals tangent theta, right? And using similar methods, we can also evaluate when k equals 5, 6, 7, or the other side, negative 3, negative 2, negative 1. All of the cases can be evaluated using what we have learned so far, when k equals 1 or 2, right? For example, when k equals 5, we have sine theta plus 5 pi over 2. This can be written as theta plus plus 2 pi plus half pi, right? So if you consider this angle here, theta plus half pi plus 2 pi, this angle is coterminal with this angle. So that equals sine theta plus half pi, right? And we already know sine theta plus half pi equals cosine theta, right? And similar thing happens for k equals 6. When k equals negative 1, you will have sine theta minus half pi. We can rewrite this to sine negative half pi minus theta, right? Then we can consider this is your angle beta. Then sine negative beta equals negative sine beta. And sine half pi minus theta, we have already learned this property previously. This is called co-function identity. So sine half pi minus theta equals cosine theta, right? That's why we have negative cosine theta here. You get it? So in a summary, when you know cases where k equals 1 and k equals 2, you can then evaluate other cases when k equals some other integers, right? So that means these are the only formulas you need to memorize. You don't have to memorize everything. Just focus on this one. First group, sine negative theta equals negative sine theta, cosine negative theta equals cosine theta, tangent negative theta equals negative tangent theta, right? Second group, sine theta plus half pi equals cosine theta, cosine theta plus half pi equals negative sine theta, tangent theta plus half pi equals negative cotangent theta, right? And last group, sine theta plus pi equals negative sine theta, cosine theta plus pi equals negative cosine theta, tangent theta plus pi equals tangent theta, right? Alright, so if you know the properties we have learned, now let's have a look at an example. Can you simplify the following expressions? Okay, let's have a look at this first one together. So you can consider this as sine. So if there are a number of 2 pi's, we better separate the 2 pi's, right? So you can consider this as 34 pi plus another pi over 2 minus x. Then we will have 17 pi plus half pi minus x, right? And 17 pi equals 16 pi plus another pi, then plus a half pi minus x, right? So 16 pi is 2 pi times 8, so that means 8 extra terms. So we can just cancel that because this angle is coterminal with this angle here, right? And we know sine pi plus a angle equals negative sine that angle, so that equals negative sine half pi minus x. Then according to cofunction, sine half pi minus x equals cosine x. So eventually we have negative cosine x, right? And of course there is more than one way to think about this question. For example, you could also write it like this. So that is sine, you can consider that as 36 pi minus pi over 2, right? And minus x, then that equals sine 18 pi minus half pi minus x. And 18 pi is 2 pi times 9. That means 9 extra terms, right? So that angle is coterminal with this angle here. So we can just cancel the 18 pi here. Then we have sine negative half pi plus x. So sine negative angle equals negative sine that angle, right? And that's negative sine half pi plus x. And according to what we have learned so far, sine half pi plus x equals negative positive cosine x, right? So that's negative cosine x. So you could use either way. Okay, how about the next one? Well, basically you can use the same method to simplify the second one. Cosine x plus, so how many 2 pi's are there? We can consider this as 56 pi minus another pi over 2, right? And that equals cosine x plus 28 pi minus half pi. And that is coterminal with x minus half pi, right? And cosine x minus half pi equals cosine negative x negative half pi minus x. And cosine negative a angle equals cosine that angle. And cosine half pi minus x equals sine x. This is according to cofunction identity, right? Okay, next one. Tangent x plus 15 pi. Okay, this equals tangent x plus 14 pi plus another pi, right? 14 pi is 2 pi times 7, so that means 7 extra terms. So that's coterminal with x plus pi. So what is tangent x plus pi? That's negative tangent x, right? Sorry, positive tangent x. Sorry, positive tangent x, right? Alright, so next let's have a look at the third group of trigonometric identities you need to know, which are called compound angle formulas. For example, if we have cosine a sum of two angles, alpha plus beta, this equals cosine alpha, cosine beta minus sine alpha, sine beta. And if you can prove the first one is true, then based on the first one, you can prove any of the following formulas are also true. Again, so I'll briefly explain why the first one is true, okay? Okay, so the problem becomes can you prove that the following formula is trigonometric identity, which means no matter what alpha and beta is, this equation is always true. Okay, I'll give you a brief explanation. So we can draw the two angles alpha and beta in the 2D Cartesian plane without loss of generality. Let's suppose this is alpha, and this angle here is alpha plus beta, and we can also draw the terminal arm of negative beta like this, and then we draw a unit circle and let the points of intersection becomes A prime, B, and B prime respectively. Okay, and then connect A, B, and A prime, B prime. You follow me? Then we can easily write the coordinates for point A. The coordinate for point A is cosine alpha, sine alpha. Did you get it? And coordinate for A prime is cosine alpha plus beta, sine alpha plus beta. And so for B and B prime. Then if you know the coordinates of these points, note that triangle OAB is congruent to triangle OA prime B prime. Therefore, AB equals A prime B prime. Therefore, we can easily use the distance between 2 points to calculate AB and A prime B prime. Therefore, we have this equation here. Expand 2 sides and simplify. This will give you the desired identity. Cosine alpha plus beta equals cosine alpha cosine beta minus sine alpha sine beta. You can have a look at this by yourself. Okay, so basically we have just proved the first identity, right? And any of the following identities can be proved using the first one we have proved. For example, in the second formula, you can treat negative theta as plus negative theta, right? So we can write it like this: cosine alpha plus negative beta. Then we know cosine, the sum of two angles equals cosine the first angle, cosine the second angle, minus sine the first angle, then sine the second angle. So that'll give you cosine alpha cosine beta plus sine alpha sine beta, right? You get it? And again, for example, if you want to prove the third one, you can rewrite this as sine alpha plus beta equals cosine half pi minus alpha plus beta. This is according to the co-function identity, right? And that equals cosine half pi minus alpha, that's the first angle, then minus beta. Then according to the second identity, we have cosine the first angle minus the second angle equals cosine the first angle, cosine the second angle, plus sine the first angle, then sine the second angle, right? And that gives us sine alpha cosine beta plus cosine alpha sine beta, right? So basically you can prove any of the following identities using the very first one. Next, cosine to alpha. So basically you can let beta equals alpha, right? You can treat this as cosine alpha plus alpha. Again, after simplification, this gives you cosine alpha squared minus sine alpha squared. Or we know cosine alpha squared plus sine alpha squared equals 1. So you can substitute either cosine alpha with sine alpha or sine alpha squared with cosine alpha squared. Therefore, we have two other formulas here that also equals 2 cosine alpha squared minus 1 equals 1 minus 2 sine alpha squared. And similarly, you can prove sine 2 alpha equals 2 sine alpha cosine alpha. Okay? And for tangent alpha plus beta, you can just use tangent alpha plus beta equals sine alpha plus beta over cosine alpha plus beta. And then using the compound angle formula to expand that. So that's the third group of trigonometric identities. Make sure you know any one of them. Okay. Again, you don't have to. Well, if you cannot memorize them, at least you should know how to get each of these identities by yourself. Okay. Okay, let's make a summary so far. So we have learned 3 sets of trigonometric identities, right? The first set of identities can always be found in the magic hexagon. So these are the easy ones. And then the second group of trigonometric identities can be summarized into these 9 formulas, right? Make sure you're able to know each of the 9 formulas here for the second step. And then the third set of identities is called compound angle formulas. Make sure you're able to evaluate cosine sum difference or sine sum a difference between 2 angles, and also double angle formula for sine, cosine, tangent, and compound angle formulas for tangent. Again, if you can prove the first one, each of the following identities can be easily inferred from the first one. Okay? And next time we'll have a look at trigonometric functions, which are sine, cosine, tangent, cotangent, secant, and cosecant. Okay? So we'll leave this to the next lesson.